Hello everyone and welcome to the third lecture of solid state chemistry, which is a very exciting lecture that totally deserves to be in the center of the whole course, in which we're going to talk about solid state batteries. As usual, we are going to split the lecture in three parts. The first one, we're going to talk about the principles of batteries in general. The second one, we are going to really go towards the modern approach to batteries, which is a completely different business, and then give some perspectives on the most performing batteries that we can have and actual improvement that we can push on the system. You can follow the progress on top of the slides with the bar telling you where we are. And you are always free to leave comments or questions on the single feedback route document that we have on Canvas. So in previous lectures, we comment on the concept and the purpose of conductivity, which is the capability of running electrons through a material. And we saw how, depending on the energetic states within the material that make you the nice bands, if you have no gap between the bands, you find yourself with a conductor that really flows electricity well. If you have an extreme difference in energies between valence and conduction band, then you find yourself with an insulator. And then you have an intermediate state in which you find yourself with semiconductor. And in semiconductors, the conductivity is dependent on temperature. But this electron hole mobility that you have can be tweaked further with doping. Now, one thing that we stressed even last time while we were talking is that conducting electricity or charges is different from creating electricity and charges. So you can conduct something if you have a potential between the ends of your material, but you cannot make this electricity. Your conductor only conducts, it doesn't create the thing that is needed to conduct. Now, the question of how do we source energy from something that is not burning coal is one of the cornerstone of all the discourse at the moment, because it's a very important and state-of-the-art pressing business. And it's not like we don't have some answers. Some of the answers we even covered in the last lecture when we talked about solar panels. So in solar panels, you expose your material to the sunlight. The sunlight is the thing that gives the energy required to create the actual charges. And then you can go and use this energy. But as we were discussing last time, this thing is something that happens and you cannot stop it from happening when your solar panel is exposed to light, and will stop happening if your solar panel is not exposed to light. So either you use all of the energy that your solar panel is giving you immediately, or there is something else that you need to do, because you will have to store this energy into something. Your solar panel will not stop with all the electrons inside and make them available for you when you need them. You need something else that will put itself in between. And as you might have guessed, the technology that we're going to touch upon today is something that is not exactly been around for a very short time. It's a sort of old fundamental chemistry technology, and the thing that you can see here is the first original battery from Volta, in which we just have this stack of material. It figure out it makes electricity. This was basically the 1800, and everyone was very amazed, but it's not a new technology. The concept in itself is not new. So what is the basic principle of a battery? What is a battery? A battery in itself is an electrochemical cell. So you want to do tricks with electricity based on the chemistry. So you need three components for a battery every time. You need an anode, you need a cathode, and you need the electrolyte. The electrolyte must separate the anode and the cathode, and it could be liquid, solid, something else, but usually solid electrolytes are used for when anything that is here on the side is a gas. Why? Because there is this point of touching, which is tricky. Why is it tricky? Because you need reactions happening here. So in your standard setup, then you have oxidation happening on your negative electrode. So you have your material over here, it gets oxidized, it gives you electrons off, and whatever is here on the surface gets, in this case, in solution and gets transported off by the electrolyte. On the other side, which is the side that is going to receive all the electrons made on this part, you have your positive electron, and the positive electron is the one where the reduction happens. So you have your material of the cathode that is going to accept electrons and accept whatever is coming from the outside. Now, the potential of this cell is dictated by the material. So a standard reduction potential is how likely is this whole process of reduction, oxidation to happen. You have standard measurements for this. We don't expect that every material will go as question mark, question mark. So you use the hydrogen reduction as your standard point. So that thing is set at 0, and every potential is calculated against that cell. So you have an hydrogen electrode, and everything else is in comparison to the hydrogen. If you have a standard reduction potential that is positive, your material will reduce better than hydrogen. If you have a standard reduction potential that is negative, your material will oxidize better than hydrogen. When you connect the whole cell, you need to remember that every point, every material has its own standard reduction potential. So it's the anode reduction potential and the cathode reduction potential. Those are standards against hydrogen, but when you want to know what is the potential of your cell, you need to put them against each other. So you need to subtract the potential of the anode against the potential of the cathode, which is equivalent to say that you want to sum oxidation and reduction potentials. And this thing as a whole will be the overall potential of your cell against standard conditions. If this potential is positive, it means that your cell by itself, the moment you connect all of the materials, so the moment there is something that changes these two, will start popping out electricity, and you won't have to do anything about it. It's a spontaneous process, and that's it. Now, as most things, when we have a standard because we don't want to recalculate every single time. So by mean of having a standard, it means that most of the stuff is actually tabulated. So you will find it in most chemistry books, and this like E to the 0 is equivalent to V0, so it's a standard reduction potential. Of course, remember, at a very given temperature, and these are only half reactions because the other reaction is always supposed to be this one, which you can see is set as 0. And if you need the reverse reaction, so you need it as the oxidation, not the reduction, you just flip the reaction, the half reaction, and you flip the sign of your thing. So this allows you to think about, okay, what can I chain here that gives me a cell that will have a spontaneous potential when I connect the two electrodes. Now, as most things that we discussed around, thermodynamics is our friend, so we need to remember that we define a lot of parameters through the thermodynamics. So once we have our standard reduction potential of the cell, it will be correlated to a series of thermodynamic parameters. So you need to remember, though, that thermodynamics as a definition of the law and a definition of what the thermodynamics can give you, is something that works at equilibrium state. And a cell very rarely goes at equilibrium. But if we go at the idea that your cell is basically at equilibrium conditions, your reduction potential will be correlated to the free energy of all this business that you have going around, and also correlated with the Faraday constant and how much stuff do you have going on. How do you calculate the free energy here? You will have to have the usual business of we want the standard one, and the deviation from the standard one relates to the concentration, but you can call it activity, depending on how concentrated they are in the solution, of everything that is going around. Because here you don't have just one component, you have a sequence of components, and all the components, as a function of temperature, are going to give you a certain capability of contributing to the general free energy of the system. So when you bring up the cell in connection and you assume it's close to the equilibrium, so very little is changing, the activity of the product and the reactant, depending on how you're calculating your cell, will be plugged into your modification of your free energy. This whole thing is the thing that you actually end up transforming by basically plugging this into this thing here. You end up transforming it into the Nernst equation, which I'm reasonably sure you also saw in basic chemistry courses before this one. So this thing is fundamentally a modification of the standard voltage of your cell based on temperature and how active are the charges moving around, and the activity of your products and reactants going around in these electrochemical reactions. Now, assuming that you have everything connected and the cell performs spontaneously, you have a current I that is produced with a voltage V, which is dependent on the cell, and this current will go on for a time that we can call delta T. But by nature of having this thing, you know that your cell is not operating at equilibrium condition. A cell at equilibrium condition is exhausted, so you want it in a deviation from thermodynamics equilibrium. So you know that this thing will not apply perfectly, but it is good for you to use to know what is the baseline of this thing, because it will never go beyond the point of equilibrium. This is a point of reference that you must be able to use, but know that the moment you connect your battery because you think it's a new battery and you want to put it in and use it, this thing will be as far away from thermodynamics equilibrium as possible. The closer it goes to thermodynamic equilibrium, the closer it goes to being exhausted. Now, why are we so concerned about the fact that we are away from thermodynamics equilibrium? Because there is a series of stuff that happens when you're away from thermodynamics equilibrium, and a series of considerations that you're forced to put in action when you know that your system is not a system at equilibrium. Most of all, the kinetic. So the issue with the kinetic is, first of all, that you're not working with point reactions. You're working with something that has a bulk electrode, a bulk electrolyte. So first of all, you need anything going from within the electrode to go to the surface. You need a mass transfer around the electrolyte going to the surface, and you need this electron transfer happening, and in this specific case you want the whatever it is to give you a a reduced version of your material by taking up an electron. So you have a series of necessary mass transport process that must happen, because if they don't happen, your cell is not working, right? So this is series of transports. If you block them, your cell has stopped working. So every time you consider the thermodynamics of your system, you have to consider this whole flow and the kinetics. So how fast are these processes, how nice do they work, and how well do they interact at the interface. This thing of the interface is kind of key for this thing, because basically the rate of reaction is what gives you the current flow, but the electron transport must be forced in the most important direction, and the mass transfer here must happen. So usually, to get the proper current flow that you want, you might have to put an additional energy into this system, which we call an overvoltage. The overvoltage is the deviation from the equilibrium condition, and this is an irreversible point of losing entropy. So you are bringing your system out of the point of equilibrium to be able to keep pushing these electrons out. Of course, another point of importance is that just like we were discussing for solar cells, this thing will not happen by itself. You need two different materials to actually have your electrode and your connection. So pushing electrons through two different materials to go somewhere else, and then from somewhere else into another material, requires you some additional voltage for this thing to happen. The sum of these two effects, so the overvoltage and the drop of potential that you have because you forced a sequence of transport in different materials, is called your polarization. So this is a series of things that you need to take into account, not because you constantly have to think about them, but because if you don't think about them, you're not properly understanding what your battery is doing and why your battery is not as nice and as straightforward as just writing a redox reaction down. Now, one of the most basic battery that a lot of you might be very familiar with, because it's a battery of your car, is the lead acid battery. And we often take it as an example because it's a very nice established battery, which is very close to the bulk image that you see in every book. So you have your anode, your cathode, and the flow. Your cathode, your anode, and the flow of electrons. And what you're using here is lead in different states. So if you go back to that table that we had, we can see what is this potential and what is this potential. In total, they do a cell that operates around 2 volt. The important bit here is that you must have acid involved in the business. So this thing will not work if you were not to have sulfuric acid concentrated, and this cell works better in a way that is almost linear with concentration of the acid. So this is another trick of thinking about transport and stuff like that. This thing in itself is reversible, it can be reversed, but remember that by reversing it, you basically want to also get rid of this lead sulfate that inevitably gets formed at the surface of your anode. So when we talk about rechargeability, we need to think about the fact that your reaction can go in 2 directions. Now, this is not necessarily always the case, because sometimes you made the reaction happen, it cannot go back. But if you have the right chaining of material in anode and cathode, it will be able to go back. Just one of them will be spontaneous and the other one will need work. So what is the general flow of this thing? The flow is that regardless of you have charge of discharge, there will be an internal resistance of the battery to the current that is going through, right? So this thing opposes the ionic current, meaning all of those specimens that are going around to get reduced and oxidized. So having an internal resistance in opposition of the ionic current will reduce the voltage. So regardless of charging or discharging, there is an effect on the voltage. So it reduces the output voltage and it will increase the charging voltage. So there is something that you need to overcome, both to make the current flow and force your cell to recharge. This thing is a function of the intensity of the discharge and the resistance of the battery, which is that factor of polarization that we were talking about before. And what you are particularly interested with when you want to figure out what is the battery that you need for your purposes is the actual cell capacity. So how much intensity in current can your battery give you as a function of time. So if you rearrange this business thinking about the fact that the intensity is nothing but a flow of charges over time, this becomes the overall charge density that your cell is able to give you out. So the total charge per unit weight and unit volume. And this thing, you will find it often every time you try to define a battery. If you try to see, like, oh, I want to buy this new phone, what will work better, you will probably see, like, also the specification of the batteries. Now, the available energy when your battery is fully charged, so the energy that is inherently stored in your battery before you plug it into anything, which is our very powerful business here, because it means that this thing is ready to go, but it will stay there and will just release this energy the moment you connect it, is basically a function of the intensity and the voltage as a function of time. Once again, though, the intensity is charges per time, so you can basically consider it to be like a function of the voltage per unit of charge. And one thing that is very important every time they tell you, like, this is a rechargeable battery, when you want to claim that you made a new battery that is better than the previous one, is not only these other two parameters, is the efficiency. So how many cycles can we go through between charges and discharges before this factor here goes off. So you want your battery to perform at least 80% of this capability, otherwise it's a battery that has a life cycle that is not appropriate. So how many cycles does it take to have your battery go down from 100 to 80%? It's the efficiency of your battery. Now, even with current, like, general standards, the way to improve a battery usually passes through a series of tricks that are on the electrode, the electrolyte, and the general setup. So for every given battery, you need to be careful about having like a reaction that is not even on your material, because if your electrochemical reaction is eating away in an uneven way on your electrode, then you will find yourself at the end of the process with an electrode that has a different shape with the one that you started with. You want your electrolyte to be able to make the charges go through as fast as possible, release them and catch them as fast as possible. So this is a point of efficiency that you can try to trick around with. And of course, you could, like, no one uses really one electrochemical cell. Depending on how clever you are in building up a module of connection of different electrochemical cells, you will have a different amount of charges per unit of volume. And the technical evolution of batteries has moved away significantly from just lead-acid batteries. So regardless of the architecture improvement that you can try to make on your battery, usually the best way to improve a battery is change what is making the battery go. So change the electrochemical effect that you have. So the lead acid battery is the oldest battery, it's the first one that they got into functioning, but the one that you might be very well used to touch is the nickel battery, and the one that instead you're incredibly familiar with, because most of the electronics nowadays uses it, is the lithium ion battery. So we're going to touch a bit on what is going on with the nickel batteries. So the issue with the nickel batteries is that they can either be nickel oxide batteries or nickel cadmium batteries, or with an hydrogen absorbing alloy as your negative electrode. The issue with like which one of these two do you use is very easily correlated with the fact that cadmium is toxic. So it is something that you don't want to easily use and enforces some issues with the process, with like actually making the battery, because it's toxic. The reactions are written here, and if you see, the one that you have on one side is always the same, depending on what you have on the other side. If you have an hydrogen absorbing alloy, so something that is basically soaked in hydrogen, so you absorb the hydrogen and now you have this metal hydride that can release this trick, or you have cadmium that just goes as a metal. And the electrolyte, which is the source of this like OH minus and H2O that you see around, is aqueous potassium hydroxide. This thing is a reversible reaction, so you can go back and forth depending on where do you push the electrons and if this thing catches or releases water, fundamentally speaking. And this thing makes it a rechargeable battery, so it's the thing that you use in fundamentally every technology of like your like the thing to switch the AC on and stuff like that. Now, what is the trick here? Like what is going on with this technology that makes it different from just using lead acid? So why do we have it as a different business? Is it just because it's basic? Not really. So the trick with nickel, nickel-based battery, is that the reaction product is not dissolved. So whereas in the lead acid battery, you have this reaction going on and you assume that you take the material into electrolyte and you get it back from the electrolyte and back and forth and back and forth, and you make and dissolve this lead sulfate, which we saw can cause some problems and some limitations to the recharging cycle. The flexibility of the structure of nickel oxide hydroxide and the fact that nickel can have multiple oxidation states mean that the whole reaction happens within the solid state. It's just your material flipping through different configurations of the structure. So the arrangement of the atoms inside is different. The material in itself is the same. So you keep your electrode steady, your electrode is vaguely changing shape, but these two things are like coherent with each other. So you can keep it at the crystal structure. So the key to this thing is the polymorphism. So it's the fact that nickel oxide hydroxide can have two different crystal shapes. And this is also something that can cause you problems with this whole business. So the one that you want to use to actually use the battery is the beta nickel oxide hydroxide that is immediately correlated with the nickel hydroxide. So what you will want to do is charge and discharge between these two, right? So you just want to go back and forth between these two. They are highly compatible. So if you look, so if you basically you have these single cells, and of course your material is made of several millions of these cells. But you want these sheets that you can see here that have very strong contact and strong bonding on the plane and weaker bonding between the two planes to be compatible with each other. You don't want a huge shift, because a huge shift will mean that your material is doing this as the cell is going on. It's not ideal. So if you manage to charge and discharge between these two, you can see that the distance and the width of these planes is basically equal, not exactly equal, but fundamentally speaking, very tiny difference. What you need to be careful with is that upon overcharge, or if there is hydration of your material, you will end up with the alpha and the gamma forms. You can charge and discharge through the alpha and the gamma form, but you can see that the parameters that you have going on here are completely different from the one that you had before. So you really change the shape, but it's just the distance and occupancy of the plane type of business. So the beta nickel oxide is the one that you want to use as a positive electrode, and you have these alternate planes. So this is the reaction that is going on. So you want this to be completely reversible and bond with the water and or the hydroxide that is coming in and out. And if you wanted, you could be able to reduce this completely to nickel oxide, which is not what we want to do, because we want to have these correlations. And the way this thing can go through charges and discharges is that it changes by moving the planes slightly against each other. You manage to change the coordination of your hydroxide that is in between. But fundamentally speaking, these two are at the same distance. If you really look at the crystal structure, even from the previous slide, you can see that one of them is slightly tilted, meaning that instead of having planes constantly stuck together like this, they also shift a tiny bit with each other to change the coordination inside. The issue is that upon overcharge, here you push water and you push potassium ions inside, and for the structure to keep being stable, you end up with a mixture of nickel 3 and nickel 4, and this thing is something that can happen because you're in alkaline solution. So once again, the water is pushed inside. You could go back to this structure if you dehydrate your alpha nickel hydroxide, but when the battery is in operation, you cannot really dehydrate the battery as it's working. So your issue is mostly that as you overcharge, you end up having this sequence of charging, discharging materials that are not your original cathode material, which is this one. Why is this a problem? Because I don't know if you ever opened something that is a very old electronic piece that had very old nickel battery. The batteries will swell, and since this thing is vaguely liquid inside, because it has this liquid like hydrated potassium hydroxide electrolyte, when it's well, it will also leak. It's a mess. Everything smells vaguely basic. Not recommended. So this thing of we have water and potassium hydroxide pushing inside of the structure is the main issue that you have with nickel batteries. But can we stop it? Is there something that we can do to stop it? Or at least, since it seems to be very eager to do this thing, can we use this peculiarity of a structure that it seems to be able to accommodate a lot of stuff inside for something nicer than just ending up with a leaky, smelly, sticky battery? This is something that we're going to discuss in the next lecture, in the next part of the lecture, as we go towards more modern batteries.